Red-black trees, as far as implementing them goes, have a really slick way of changing the representation to kind of make it algorithmically simple. But it doesn't necessarily entirely intuitively connect to the representation we saw in the 2-3 trees. So a little bit what I want to do here is to talk about what that connection is. So we talked about the idea of this two values, three children, left, right, between. So moving to the red-black symbology of this, a red node indicates this relationship. So L and Q as being, the two boundaries with some stuff in between can also be represented by single nodes where L becomes a quote unquote red node. That relationship between Q and L is marked as being red. And so the left leaningness that we try and put into the red-black trees, that's the phrase that's often referred to, is saying that we're okay with having a red, but we want the red to be on the left side. Now, another way we can represent this in the drawing is by putting these, instead of vertically spaced, we can put them horizontally. So anytime you see a red node, you could draw it as LQ. Now, I'm not going to do that going forward, but particularly the book notates this as a way of being able to draw it, and it really does help you start to think of as you can see here, the LQ horizontally together is very similar to the LQ as being in the same node. All right, so when you think of something is red, and you're going to see that a lot in the algorithms, it took me a while to do this, and I'm probably still not all the way there, but just think of this as being a 2-3 node as opposed to a 1-2 node. So instead of a one value with two children, you can think of the red as linking the two values between the nodes and having, in theory, three children, where essentially the right node of L becomes the stuff that's in between L and Q. It's greater than L but less than Q by definition at that point. So let's look at how we codify this redness. Again, the idea, very simple. We have the basic node. It has a value, maybe a key value if you're dealing with maps instead of sets. But then you have a left and a right, and then this idea, is this node a red node or not? It's not, is the left or right link? That's up to that next node you're connected to decide if it's red or right, red or black. But it's the red is the relationship between the parent and this node. So just that really simple Boolean value is all it takes to turn our regular tree into a red-black tree. Now, that's other code changes that's going in, but as far as the data, that's all we really care about. And some trees, you'll be tracking the size as well. I don't know if there's a lot of utility in the size. It doesn't really change the algorithm, or we don't make any decisions based off of size, but it's something you can track in the node along the way to see what the size of that subtree is. All right, so as we talk about the operations that are specific to the red-black tree, there's a couple basic things that we deal with in basically both remove and add. So we're going to rotate nodes, and we can rotate to the left, we can rotate to the right, we'll talk about that in a second. We can flip the color of nodes, so now that we have red and black, we can switch what the color of a node is by changing the children's color and the node itself. And then we have this idea of balancing. So the only time we need to balance a tree is when we're either adding or removing values from it. Just simply looking something up or navigating the tree doesn't change the structure at all. So the balancing is going to be something that's going to be exclusive to add, remove. So let's look at this idea of rotating. So the first thing, as we said, we want to have this notion of leaning left. So if we have a situation where a right child is marked as red, so instead of, in this case, we still have this betweenness. M is between L and Q, but we don't prefer that. We prefer to, as I said, lean left where the left children are going to be the red ones. So in this situation, we can handle it by rotating to the left. And so when we rotate to the left, we want to say, okay, well, we actually want L to be the left child, and that's going to end up being red. And we want Q to be the parent, and then M is going to, being between L and Q, is going to be the right child of the, in this case, the node L. So the parent becomes the child, and the child of the child becomes a child of the parent. And so, quite simply, we make that quick shift. As we can see, the Q was the child, and now what was the parent becomes the left child of what originally was the right child of Q. And then the left child of Q becomes the right child of L. And so conceptually, it should make a ton of sense. Either way, M is always between L and Q. What we're just switching is the hierarchy inside of how this rotation goes. But notice here, the important thing is when I rotate, I could be shifting who the parent of L should be pointing at. So there's going to be a lot of cases here where recursively we're going to be returning nodes, and who used to be your left child might change because you have called any of these functions for add, remove, rotate, and a bunch of those functions that are going forward. So rotating right happens for a different reason. Again, we rotate left to keep our rule of left leaningness. We rotate right when we end up with this multiple reds going down the same path. Sometimes it's a red, red, left. Occasionally we'll actually see in the algorithm we'll have a right child that's red and then its left child that's red. That will lead us to some rotation as well. But those are reasons to rotate. The mechanisms of rotating are the same, basically the same concepts as we saw on the left. In this situation, though, what we don't want is that 3-4 node. That's kind of what this is representing. To say, hey, we have values between L and M and values between M and Q, and those are separate. So we're going to go back to a more traditional 2-node or 2-3 node, 1-2 node or 2-3 node relationship. So now that we've seen, okay, left is right red and that child's left is red, then we can say, okay, well, let's just simply rotate right. So Q becomes the right child of M, and then whatever was the right child of M becomes the left child of Q in place of M. And so then again, we're balancing out that tree again. We're making sure around M there's a similar number of things to the left and the right, and that rotation then again keeps us our left leaningness without having a 4-node things between. All right, so that is a little bit of concept. So let's see where this falls into place. These two functions are really, really important for when I want to go balance a tree. So balancing a tree is basically a reactive process after I've gone through and either added or removed a node. We're going to find this is the process that gets called basically at the end of it. There might be some proactive stuff that happens before we get to that point, particularly in remove. Often we'll see in a later video, in remove, we'll set up the tree to be balanced as I prepare to remove something. But balancing a subtree has one other little feature that's important. The other little sub feature inside here is the idea of flipping. So flipping is another function that could stand alone on here. And basically what it is just saying like, okay, we've ended up with 2 red nodes of a parent, and instead of having to move stuff around, it's not necessarily a problem. What we do is just simply make those 2 black and make the parent red. We're just flipping all these things to be the opposite. So M becomes something that, is now part of its parents' relationship, and then Q is between obviously M and whatever's up above, and by definition, but we now are basically balancing that back out. So flipping is the last piece. But let's talk about the rules of balancing in general. The first step to balancing is make sure your tree leans left. So if your right node is red and your left node is not, you need to rotate that to the left. Now, if they're both red, we can flip it later on. That's not a big deal. But and by the way, the balancing works on a single node, and the balancing works essentially bottom up. We start at the bottom of the tree and we balance it by starting the bottom and move our way up. So everything propagates its way up, and we might be moving things, from the bottom up. We don't move things top down. We don't know until we get to the bottom how big any of the tree is, and so where things need to move. So again, if the right is red, we need to rotate that left, and we saw how to do that we move that node. The values aren't important at this point. We make our tree lean left at this point. Now notice we might be actually unbalancing the tree by moving that. We might be moving this up, but we're not done yet. Once we've moved this up, again, we're going to return the call to the parent. The parent's going to evaluate what happened to its node, if it's red or whatever, and then it's going to go through and make that choice. So step one, lean left. Step two is deal with any of these between values, this four node situations. So if I have two nodes to the right, then I need to rotate right. So you can see the rotate left, rotate right. Immediately, we're going to make use of these two. Again, we rotate that right. And again, you can see we're now balancing it back down. So we propagate some things up, we bring some stuff back down. And then step three, we check the colors. If we end up, and we don't always do, but if we end up in a situation where the two children are red, then we flip the children using our flip colors, and that node becomes red. Again, the one thing I really want to iterate through all these calls, they're recursive and they return a node, and the root that came into a recursive call might not be the root that gets returned from the recursive call. When I am dealing with a standard binary search tree, the first value added becomes the root and stays the root forever until it's either removed or basically until it's removed. Either it can be removed before the tree, or the whole rest of the tree could be removed, but that stays that root. Here in a balanced tree, that root might change, probably not every call, but every handful of calls it might be changing. So given these core pieces, rotate left, rotate right, flip, and their use within balance, the add function becomes actually ridiculously straightforward. We have to implement each of those three, but to add to the tree, it actually goes just like we had done in the binary search tree. If it's less, add to the left. If it's greater, add to the right. If it's equal, if you're set, you can skip it. It's already there. If you're a tree, you replace the value. And then after you've done that normal search behavior, balance. So the start of adding to the tree essentially starts with the same add algorithm you had before, and you just start implementing the balance method we just saw. Now, I'll remind you, the purpose of this video was not to give you pseudocode that you're supposed to reverse engineer. The book sketches out the add method, and it shows you all the balance methods and everything else like that. So pull them in and use them. Feel free to use whatever resources you want to build this code. Use this video to conceptually understand the purpose of these methods and what they're doing, how they manipulate the tree, why this 2, 3, 3, 4 node combination ends up with this red-black, this logic, and how that goes. All right, so have fun getting started with that. You might want to play with this for a while before taking on the remove/delete. That's a pretty complicated algorithm, but that's going to be the subject next time.